Hello, and a warm welcome to our webinar goes out today to our customers, students, power electronic engineers, and last but not least, to our competition. My name is Emilio Meza, and I'm your moderator for today's webinar titled More Compact and Efficient Motor Drives with Silicon Carbide. With recent technological advancements, silicon carbide is becoming the first choice for enabling energy savings and increasing power density. However, motor drives and silicon carbide MOSFETs are two topics that once seemed impossible to combine. High costs, fast switching, lack of short-circuit capability, and reliability concerns were all persistent roadblocks, preventing a tangible return on investment. But it is time to update our thinking. By merging state-of-the-art packaging technology with the latest generation of SiC MOSFETs, Semikron Danfoss provides a totally new degree of design freedom to motor drive design engineers. Before we get started with the presentation, some words about our webinar platform. In case of connection issues to the presentation stream or to the sound, please try to reconnect by refreshing the browser window. In your browser, on the right-hand side, you see the question window, which you can actually hide to increase the screen space for the presentation. In case you have any questions about the content or technical difficulties, please let us know via the question box. All messages are private, and only we can see them. We will try to answer your questions at the end of the presentation. The questions we do not manage to answer today will then be answered by email during the coming days. Also, you can send us an email to webinar@semikron-danfoss.com at any time, and we will get back to you as soon as we can. Lastly, we will share the presentation as a PDF at the end of the webinar. Your presenter today is Carsten Schreiter. Carsten received his degree in electrical engineering at HTW Berlin before joining Yaskawa in 2000. After a career in applications engineering, development, and product management in drives, Carsten joined Semikron, now Semikron Danfoss, in 2022. He is now a senior product marketing manager with a focus on the drives market. Enjoy the webinar. Carsten, the floor is yours.
Thank you, Emilio, and also from my side, a warm welcome to the audience out there. Today, we're going to talk about silicon carbide and motor drives, how it can be utilized, and what benefits we can get from utilizing it in the motor drives. If you look at silicon carbide, it's not brand new. It's been in the industry for a while, and it's used in many, many applications. I have some examples here, like solar, where we use it for power density and efficiency, and charging for making small chargers powerful in cars, electric cars to increase the mileage or the reach with a given battery capacity. But if you look to motor drives, then there's not much happening. I would compare it to a little tender plant that is just barely leaving the ground, but not really growing yet. And the question is, why is that? Well, if I talk to customers or to people from the industry, then what I hear many, many times, I listed up here. So some common assumptions, I would even call them some myths about motor drives and silicon carbide. So what I hear very often is it's too expensive and it will never pay back in a drive. Many people also think it only makes sense to use it when we talk about fast switching, so high carrier frequency or fast DVDT. Many people also think that only high DVDT is possible with these kind of switches. What we also hear often, application reliability is not given. Then most of the time, short circuit is an issue, which is a must in motor drives. You can't sell any or build and sell any motor drives without having a certain degree of short circuit capability. So many people think that is not given with silicon carbide. And all in all, we often get the myth, the assumption that it's just not usable for motor drives. Now, we can guess already that I don't agree. Otherwise, the webinar would end here. I will tell you why this is. Why I don't agree to those things. Why we think silicon carbide is the right material for being used in motor drives. Here's what we will go through today. So I will start with talking about why silicon carbide makes sense in motor drives, where the difference to silicon and IGBTs. I prepared 3 application examples where I will show you the benefits and how they would turn out in practice. I will give you some insight into products that we offer for this market with silicon carbide, and we will finally conclude. So let's go. Why should we use silicon carbide? The first thing I want to highlight here is the 4-watt voltage drop. And if we then compare IGBTs and silicon carbide, like we can do in that chart on the right here, We see here that the blue line, that is the forward voltage characteristic of a silicon carbide MOSFET. It's almost a straight line, while the IGBT has this curve here. And what we see from the chart is that, for instance, at a given current, let's take this one here, the MOSFET would have a forward voltage drop of, let's say, 1 volt, while the IGBT at the same current has 1.5. And this reduction in forward voltage drop, that actually reduces the conduction losses, and that gives big benefits and drives applications, especially when we are in the lower load area here. I try to highlight this by this shaded area here. Keep that in mind. That's an important fact for the following slides. Then what we also have, that the embedded body diode, the reverse recovery charge there, is much lower than the one that we would have in a freewheeling diode that is paralleled with an IGBT. So you can see that in the lower chart here, there's a factor 10 between the reverse recovery energy between the body diode of a silicon carbide MOSFET and a freewheeling diode that we put in parallel to the IGBTs. Then in certain applications, we can also use the reverse conduction capability of the MOS channel, which then reduces the temperature swing in the junction. And reduced temperature swing and the junction means higher capability of power cycling. So that really impacts the lifetime and the power cycling capability. We must not switch faster, that you will see also on the slides, but if we want, we can do that. Thanks to the unipolar channel there, we can go up to high carrier frequencies, but as I said, it's not a must. The material itself, silicon carbide, has a much, much better thermal conductivity. That means that the heat spread within the chip is much more even than if you compare it to an IGBT. You don't have heat spots in there. And that, again, is good for the die connection to the DCB, good for the lifetime of this connection. And last but not least, and a very important fact, is that the latest MOSFET, the silicon carbide MOSFET chips as we use them, they provide short circuit capability. That has not always been the case. Earlier generations didn't have that. And that's why they were probably not usable in motor drives. But the latest generations can do it. 2 microseconds is not the same as an IGBT would offer, but it is at least something, and it's manageable. So that's also an important fact. And if you look at it all together and think where we can use it in a drive, then really some benefits come out of here. So what is the application in a drive? Typically, it's either on the front end, if we have an active front end drives. Normally, the standard drives like they are today, most of them use a 6-pack there with IGBTs, very low carrier frequency, 5 or 6 kilohertz. With that, there's always the need for a big filter here to filter the harmonic currents, which then consists of a choke, capacitors, sometimes resistors, and another big choke, a lot of copper and iron here, heavy and big. And most of these solutions come even with separated filters and converters and then inverters. So you have 3 different units. There are a few solutions that have all embedded, but not too many. Why we do this? Of course, to comply with grid standards like the IEEE 519 or others. The other application area in a motor drive would be the motor inverter, the output side. But here also we have some limitations, and we have to keep them even when going to silicon carbide. Typically, the motors have a limitation in respect to the voltage rise time. We should not go higher than 5 to 10 kilovolt per microsecond. Kilovolt 10 is already pretty high. This is to avoid overvoltage at the motor terminals when we have reflected wave effects with long motor cables and these things, not to burn the motor winding. So 5 is normally the limit that it's used in the industry. And then also the carrier frequency is typically set to 4, maybe 6 kilohertz. For standard, you can go higher, but then the cable length is a limit. Shielded cables can create issues with high carrier frequency and all these kind of things. So there's this limitation in voltage rise time, and also the carrier frequency cannot be boosted up to high values. And even if we go to silicon carbide, then we have to think of these things, but still it makes a lot of sense. And why and how, that I will explain when we look in the examples, at the examples here. So I will start with the active front-end example. Active front ends, they are more and more common, or they get more and more popular, I would say. The reason is, of course, we electrify more and more. We use more power electronics, and then if we come with standard B6 bridges or something like that, then the harmonic content in the grid is pretty high. It's a burden for all the components in the grid, for the grid itself, and then of course we should put some effort to reduce the harmonic content. And the natural way is to use an active front end, as it's drawn here. So 6-pulse input bridge with IGBTs. And that big LCL filter that I mentioned before is usually used. And to see what we can optimize here in such an application by using silicon carbide, I made a comparison. So here's my grid condition for this active front end. I say it's working at 750 volt DC. My grid voltage would be 400 volt AC. The phase current, 30 amps. Cosinus phi is 0.98. You see that's a harmonic a low harmonic solution because we have positive cosine phi, but even if we go to regenerative action, that doesn't change. And the grid frequency is 50 hertz here. And what I then did for the comparison, I used for this module part here, for this active bridge part, generation 7 IGBT, rated for 50 amps. And I then selected a silicon carbide module, same rated for the same current, also 50 amps. For the silicon carbide to reach basically, or to get to a similar thermal condition, similar junction temperature, I quadrupled the carrier frequency. So the IGBT version, I calculated or simulated with 5 kilohertz, as it is used nowadays in many cases. And the SiC version, with the SiC version, I went up to 20 kilohertz here. And then I used our simulation tools, which is called SemiCell. That's a free simulation tool that we have on our website for doing thermal simulation with all our products in various applications or all the topologies that you can think of, anything that we offer. I used this tool and made a comparison for the converter, and I also made a comparison for the filter, because naturally when we increase the carrier frequency, this filter also changes. And the result you can see in this table. So if you look at the converter first and the watt losses in the converter, the upper row here, silicon IGBT, you see that we have almost 250 watt losses in the converter and 463 in the filter, means the total assembly has 710 watt losses with 30 amps. If we go to silicon carbide, then the converter losses greatly drop, 175 watt, and also the filter losses drop, 291, in total 466. That means just in the converter and the filter, we have 34% lower losses, 34% more efficiency, just by switching to silicon carbide and increasing the carrier frequency a little, so factor 4. As I mentioned, the filter can become a little bit smaller when you increase the carrier frequency. And it's actually not just a little bit, it's quite a big bit. You see the upper here, that is these boxes that would be the grid filter and the converter side choke. They would have over 8,000 cubic centimeters in volume. And if I go to the carrier, to the silicon carbide solution with 20 kilohertz carrier frequency, we have only 2,448 cubic centimeter, which means the volume goes down for 70%. That's quite something. And then, of course, naturally, if the volume goes down, you see that on the last column here, then also the weight goes down. And we have almost 50%, 74% lighter filter components here compared to the silicon solution. That is something. And if you now think forward, what that means in the application, that opens plenty of options here. You can have smaller, more compact machinery or panels if you put it into a panel. You need less cooling in your panel. Panel cooling is very expensive, and if you can reduce that, you can save money there. Less panel space or floor space when you put the panel somewhere in the production, that is also a really valuable space there. You can reduce that, or you have easier possibilities to integrate everything in one drive. So have the filter, the active front end, and the motor side in one drive, much easier, and will give you smaller solutions here. Increasing the carrier frequency, of course, also reduce the audible noise and the magnetics, if that is a factor. And also the total cost of ownership go down. So you have the energy saving aspect here, which reduces, of course, the energy cost if you save them. but also CO2 emissions go down if you care about those. Then also the smaller and compact shape and the lighter weight, the lower weight, that reduces warehouse cost, storage, but also transportation, because you can just put more on one pallet and the whole stuff is still lighter. And also when you mount these active front ends, then when you need a forklift for the old solution, you might be able to do it with one or two guys, strong guys, without special tools when you do the mounting. So there's many efforts, many benefits that you can get out of this. And this example was just adjusted to the 20 kilohertz were just selected to meet the thermal conditions of the IGBT. It's not optimized. You can even optimize the carrier frequency and find the sweet spot between size and of the choke and everything that is in that system here. But what you see from here is that it's really important to consider the total system when you think about silicon carbide. If you take just the module and put it next to the IGBT module and then compare the prices, you will of course find that the silicon carbide module is more expensive, and that will also remain this way. It will not change soon to be at the same level or be cheaper than the IGBT. But it must not, I think. If you look at the complete system here, then you will easily find that the silicon carbide module brings you so many benefits that it easily outweighed the higher cost. Yeah. So much that's about the AFE solution. Let's look at the standard inverter part, the output side. And here for the first example, I used a pump application, a centrifugal pump. For the simulation, I did a similar thing here. Basically, I used an IGBT module with a 7th generation IGBT, and I used a silicon carbide module with the latest generation of ROHM silicon carbide chips in there. Then I use a standard motor here from company VEM, PM motor, as you can find them in the catalog with these data here. It's a 15 kilowatt motor. My drive conditions, 460 volt, 5 kilohertz, 5 kilowatt per microsecond. So really not in any way, not boosting or squeezing silicon carbide in any way. Ambient temperature would be 50 degrees and overload capability 110% per 1 minute. So this is a typical normal duty application, like a fan or a pump. I use this because if you look in the industry, then most of the axes that you would find there are probably fans and pumps. If you look at those, then important is to look at this torque curve. Torque is directly coupled with the current, and the pumps or the fans, they normally have such a quadratic torque curve. So you see at 100% speed, you have 100% torque, but as you go down to 50% speed, you have only 25% torque. And that is the same for the motor current. So when we are in the light load area, and I try to highlight that here by the blue box, none of the pumps or the fans that you find in the industry are full-time running at 100%. Most of them are controlled, PID controlled by flow or by pressure or whatever, so that they operate in an area where I would say 40 to 80, maybe 90%. That's the main operation area of such a pump. But then you see the current is not at the rated point anymore. If you now remember that chart that I had in the beginning with the forward voltage drop, then you see that in this example here, we're constantly working with lower forward voltage drop, and that means lower forward losses in the MOSFET if you utilize a MOSFET. And to compare what that means in the application, again, I choose two modules, IGBT module, this one here, 35 amps rated generation 7 IGBT module in this Semitop E2 package, as you can see it here. HPTP, that means high performance thermal paste. It's an option that you can have from us with pre-printed thermal paste on the module when we deliver it. 35 amp in a CIB configuration. And for comparison, I used a similar one, same package, 18 milliohm ROHM Gen 4 chip in there, also CIB configuration. And then the conditions are the same for both, 5 kilowatt per microseconds, 5 kilohertz carrier frequency. And when I then compare the modules, what comes out is this. Best as we look at this chart on the right here, so the gray colored curves are for the silicon carbide, red colored curves for silicon, IGBT. And the dotted lines is efficiency, the right scale. The solid line is left scale, power losses. And it's quite obvious what you see here, that in the complete operation speeds or load range, in this application with the silicon carbide, we would have much lower losses. That means in that operation range that I mentioned, 40 to 80%, we have roughly 40% lower losses, up to 40%. And looking at it from an efficiency point of view, we have up to 1% better efficiency on the module here. Again, simulation was done with SemiCell. And the cooling was also identical. So really, it's the same thermal concept, just changing one module to the other, and this is what you see. Quite some change. Then I went one step further and thought, what would it mean in a real drive? And to do that comparison, I used this Danfoss drive here. I used that because there's nice energy loss calculator on the website of Danfoss, where I can do nice calculations and do these kind of comparisons that I wanted to do. And what comes out here is the first thing, when I run the pump or my pump application that I used here at full speed, the energy, the losses would go down by 22%, which is quite something. And also, if we have a look at the complete speed range here, so that's the same chart like on the page before, just for the complete drive, you see that we have still a reduction of the watt loss up to 22%, which is a number. And the efficiency can also go up to by 0.7% at the max. That is something, if you consider that normally the drives nowadays, they have 99.5% efficiency. If you can increase that by 0.7%, that's quite something. And just by changing one module to the other, not even playing with DVDT or any other parameters there. I then went one step further and thought, what would it mean that lower energy consumption in a pump that is running for 1 year? So my assumptions here, price difference when I go from silicon IGBT to silicon carbide MOSFET would be for the end user, not for the producer or for the designer, but for the end user, maybe 60 euros, somewhat in that range. The energy cost in Germany, it's 20 cents per kilowatt hour for industrial use. Unfortunately, not for home use. It's a high price. If you go to America, it's only 8. But if you go to Italy, it's 34 cents. So depends a bit on the region. I choose Germany. And I use this kind of operation profile for my simulation. So I say that 10% of the time, there's no load. The drive is actually in standby. 5% of the time, my drive would run at 40% load. Then roughly 17% of the time, it would run at 50% load and so forth. And if I use this load profile and accumulate the losses over 1 year, then what comes out, you see here. So IGBT losses is roughly 650 kilowatt hours in 1 year, while the losses on the IGBT drive is only it's 42% lower. That's quite something. And these 42% I can translate into CO2. That is 127 kilograms CO2. Or I could also turn this into money with the energy cost that I used here, 56 euro per year savings. And then it's interesting, if you look at that 56 euro here and the cost adder here, you see it's almost the same. So in a little more than a year, 1.1 year, 1 year and 1 month, you have the money back. And from then, the application would actually save money. 13 months, I put it here. And of course, if the energy cost is different, then the payback time is faster or slower. I mentioned America, 8 cents. It's still less than 3 years. Or in Italy, with over 30 cents, it's 8 months. So you see that, again, here looking at the big picture, considering the total cost of ownership, the energy cost and everything that is involved, silicon carbide is definitely the better solution and the lower cost solution in the end. I played a bit more with simulation and tried to find out how else I can tweak or what else I can get out of it. And here's a simulation that I did with identical power. So I said, if I set the power or draw power from the IGBT module and the silicon carbide module and run both at the same junction temperature, how much can I reduce the cooling on the silicon carbide side? And the result is impressive 71%. The heatsink can be 71% smaller in volume. Still, I have the same power out of the module here. And if you think that further, that can also bring a lot of benefits. Of course, the cooling effort is reduced. You have lower airflow there. Lower airflow means less fans, also means less contamination in your panel or in your drive. Lower audible noise also. You could also utilize it for making higher IP rated drives like an IP55 or IP56 or IP66, because you have less modules, less losses in the module, less losses inside that drive, and that will help to make it smaller, more efficient. And also that smaller package would give a lot of benefits through the whole supply chain by having less warehouse space and less more drives on one pallet, so the shipping becomes more efficient in the end. The second thing I did is I checked if I don't change the cooling concept, so I leave the cooler, the heatsink the same on the left and on the right side, how much more power can I draw from it? And here also impressive 25% is the result, 25% more power. And that means from the same thermal design, I can probably get one more electrical frame of drive. So if I have a drive design for 5.5 and 7.5 kilowatt in the same mechanical frame with silicon carbide, I might be able to squeeze out even 11 kilowatt from the same thermal design, which offers nice possibilities for the design and makes design and testing and everything much easier. The last thing we can do is also increase the carrier frequency. By that, motors run more efficient. You have less motor losses. You have less noise there. Smaller magnetics if you use magnetics on the output. And in the end, build more efficient solution. It can also be very interesting for high-speed applications like compressors, spindles, and all these kind of things. But again, for all of these, look at the big picture and you will find that silicon carbide is, in many cases, the better solution. Also, the more cost-effective solution. The last application that I want to look at is a servo application here. I used a typical pick and place thing where something runs for 500, accelerates for 500 microseconds, runs steady speed for 2 seconds, decelerates for 500 milliseconds, stops for 2 seconds, and then the same in the opposite direction. That could be a pick and place gantry application. It could also be an application like this robot here, which is putting one part from one side of the production to the other or to the car here. So it's moving things forth and back. And for this simulation, I did the same thing as before. I used some modules here, 50 amps rated generation 7 IGBT module and 80 milliohm silicon carbide module here in the E1 package, Semitop E1. And the requirement here was a certain number of power cycles. I used the same DVDT for both, 8 kilohertz carrier frequency here because they normally run a little higher, DC voltage of 560 volt. And then I used, again, our simulation tool to do this thermal simulation. And what comes out is that if I go from the IGBT to the silicon carbide MOSFET, then the losses go down for almost 50%, the average losses over these cycles here, almost 50% lower losses. 1.6% higher efficiency. That's quite something. As I said, also the servo drives, they are normally running on very high efficiency, but if you increase it for 1.6% on this cycle, that's quite a number. Translated to money, it means 35 euro per year in this application, or CO2 reduction 78 kilogram. That doesn't sound a lot, but if you think of in a machine, you easily have 6, 7, up to 10 servo axes, or in a production, you have hundreds of servo axes that work together. And if they can all achieve this kind of savings, some more, some less, there is a considerable number that comes together here. And also here, by the lower losses, you can reduce the size of the servo. So there's many, many options that it offers you if you just look at it in the right way. We, of course, have some products that we offer for these applications. And those I want to highlight here. So we see that here we have different topologies, the CIB topologies that are commonly used in drives. SiC packs that are commonly used in drives, but also on the server applications. And then for the higher power area, also some half bridges. They come in the Semitop E1, E2 package. You see that here in 36 and 18 milliohm. And also in the mini-skip package, our famous mini-skip, we recently put in silicon carbide with 36, 18, and 6 milliohm. That would mean translated into current up to 150 amps. The same for 6 packs here. And with the half bridges, we even go up with up to 450 amps in the common or the well-known Semitrans 3 or 62 millimeter industry standard package. I mentioned that already. We use the 4th generation of SiC MOSFETs from Rome, and these come with some cool benefits. One is the unipolar switching, so you don't need negative voltage here. You can safely switch them with 0 volt off and 18 volt gate voltage on without any risk of parasitic turn on or any kind of these things. So that is a safe switching with unipolar gate voltage. And then I mentioned that also in the beginning, they provide short circuit capability, 2 microseconds at 150 degrees of junction temperature, 720 volt DC bus, and very important, 18 volt gate voltage. So the full gate voltage you can use and still have the 2 microseconds short circuit capability. That is not the case for all silicon carbide MOSFETs that you find on the market, but here full gate voltage, full short circuit capability is given. In our data sheets, we also put the short circuit energy. So if you have different conditions, lower temperature, lower DC bus voltage, then you can recalculate back to the short circuit time. It will be longer in these cases because really the energy is the limit in the end. But that we have in the data sheets. The 6 packs and the CIB modules that we have, they are pin compatible to IGBT modules. That means if you have already one of these modules in your application, a mini skip or something, then it's quite easy to take it out, put the silicon carbide version in, adjust the driver a little, and then you can already play with silicon carbide just to see what it can help in your application. It makes it really easy. The mini skip comes with sintered chips. That means that's on one hand very nice for the lifetime. It prolongs the lifetime, and then also you can run the chips up to 170 degrees continuous with that sintered modules there. And all of them provide some superior thermal performance. The Semitop E by its housing, where we use the plastic latches here, and we have a pressure system that provides almost or up to 20% lower RTH compared to industry standard packages here. Same with the mini skip with this unique pressure system here. It's also much better than comparable standard packages in the market. And the Semitrans, where we use better substrates to reduce the RTH. All of them provide superior thermal performance to really get the best out of these MOSFET chips that we put in here. One word about the thermal interface material. I want to highlight that also. You can order all of these modules with pre-applied thermal interface material, and here we have 2 options. One is the HPTP, high performance thermal paste, that I mentioned in the application examples already. But there's also another interesting material that we just recently, or maybe a year before, released. That's HPPCM phase change material, high performance phase change material. And the interesting thing here is, it's like a wax. So when it's cold, you cannot smear it off with your finger or anything. It's pretty good for handling and the production. You cannot destroy the TIM layer that the modules come with easily. And first, when you heat it up, when power is applied and the module heats up, then it gets liquid and distributes under the DCB. And that phase change material has a thermal resistance which is almost as good as the best heat paste, and that makes it really a good alternative to paste here. Just to highlight those. We come to the conclusion here. So if we look at it, I think it's pretty clear now that silicon carbide really provides a lot of new degrees in freedom when you design a drive. I try to visualize that in these circles here. So if the red circle, if that is the borderline or the limit that we have in IGBTs when it comes to space or weight or cost, or then in all aspects, the silicon carbide extends this line. If you think about the space reduction that we had for the active front end or for the drives when we reduce the cooling, the heat sink, or the material content that is reduced again in the AFE or on the drives, the cost benefit that it can provide, the higher efficiency that also gives you better or lower CO2 emissions, which is a factor that is getting more and more important. When talking about drives and when talking about industry applications or the increased power, there's probably more, but these are the ones that I looked. No matter what aspect you look at, the silicon carbide solution can provide really substantial benefits here. And the key, and that's why I think it's that choice for motor drives. Just the key is to look at the whole system and not stop with looking at one module and comparing the price to the other module. That's the totally wrong way. If you do that, you're lost. If you do it the right way, look at the complete system and all the benefits that you get out of it, then the story flies, and you will see that silicon carbide is the better solution here. So coming back to the slide that I started with, I think you agree now that all the assumptions that I hear all the time, just yesterday I heard it again in a customer meeting, the stuff that we hear all the time is really not valid, and you have to think through to see that silicon carbide is the better choice here. Some words about Semikron Danfoss and why we are your ultimate partner when it comes to silicon carbide. We are the largest chip-independent semiconductor module manufacturer, and that gives us the possibility to really choose the right chip for the application. For the motor drives application, we believe that the Rohm Gen 4 chip is really a superb choice, and that's why we put it in the modules that we use there to provide the best performing package that you can find on the market. We have also strategic alliances with our suppliers, and that doesn't mean we just buy the chips there and put them in our modules. It starts with the development of the chips. We have access to early sampling. We can give feedback, and by that impact the chip development. And it also means that we have long-term agreements to really secure the supply of the chips and the modules in the end, to have a secure supply long-term. We did not just start with working with silicon carbide. We've been doing it since more than 15 years. And also the sintering that I mentioned for the mini skips, we've been doing since more than 10 years. So it's almost a standard for us to sinter chips and provide the best performance there. We have all the packages that the industry uses, the standard packages at hand, and can put our topologies in there as customers desire. We have a lot of technologies at hand, packaging technologies that can provide substantial benefits compared to other packaging technologies that you find in the market. Sintering is one of these, but there's more. And last but not least, we have a great application team that also supports customers when implementing new modules, and that also will help you with all the competence we have when you go the step from IGBTs to silicon carbide. With that, I'm at the end of my presentation, and I think we're open for questions now, right?
Thank you very much for that great presentation, Carsten. Yes, so I actually added the PDF version of this presentation to the handout area. So if you go to the area listed either apps or more with 3 dots, you can find the handout area and download that PDF. And of course, we do have a number of questions. I don't know that we're going to get through them all today, but we can certainly start. So let's see. There was a few that overlap, so I'll do my best to cut down on this. And I think one question that was asked a few times, and maybe you can just speak more about it, is the 2 microsecond short circuit capability. So what all does that include? If you have like a soft turnoff or something, is that included in the 2 microseconds, or what can you tell us about that?
That's a good point. Well, as I said, we have these limits that I gave. The 2 microseconds, they're valid for the 720 volt DC voltage and 18 volt gate voltage, and also 150 degree at the junction, Celsius at the junction. And that gives you a certain limit in energy that the switch can handle. And if you exceed that energy, then it blows up. So you have to make sure that no matter how you switch it off, that you keep within that energy limit, and then it is safe. As I said, we put that in the data sheet there, and from that value you can go and choose whatever you want.
I have another question about the freewheel diodes, asking if they're also made of silicon carbide, but I recall that you were saying that there were no freewheeling diodes on some of these devices. Maybe you can speak more about freewheeling diodes and silicon carbide.
Yes, exactly. In the silicon carbide MOSFETs, we don't have an external freewheeling diode. The MOSFET always by its structure has an embedded body diode, and that body diode that we use as the freewheeling path. So we don't use external diodes as we know them from the IGBT world. They're just not necessary here.
Okay, but we do also have those modules you mentioned that have IGBTs plus silicon carbide Schottky barrier diodes as the freewheeling diodes, right?
I can almost say we had them, because it turned out that they are not a cost competitive solution. Having the full SiC module nowadays is more cost competitive than putting an IGBT and put a silicon carbide Schottky barrier diode next to it, and then with all the bondings and the soldering and whatever you need there, it's just not cost competitive to the full SiC solution. I would never go for anything else than full SiC nowadays.
Okay. I have a question here so if we're replacing an IGBT power module with a silicon carbide power module, that it may not be just a simple plug and play replacement. Are there any considerations that need to be taken for changing from IGBT to SiC MOSFET?
Of course, it's not a simple plug and play. There's some things, of course, the gate voltage is different, right? I mentioned for the chips we use, you have 0 to 18. If you have an IGBT that switches -5 to +15 or something, then obviously you have to adjust your gate voltages a little. The gate resistance will also be different. Naturally, the chips are made for fast switching. To slow them down to 5 kilovolt per microsecond, you need normally relatively high gate resistors, but that's doable. But that's more or less the only modification you have to do unless you want to go for fast switching and all these other things that we didn't even look at today. So it's really these things: gate voltage and gate resistors, and then you can try playing with it, and maybe your short circuit detection if you want to test that in the first instance. But yeah, that's it basically.
Okay. And then I have a question about for our portfolio, what is the maximum voltage ratings that we offer in silicon carbide?
At the minute for the motor drives with this ROHM chip here, it's in the 1200 volt range.
Okay. But I will add, if anyone out there is interested in 2000 volt silicon carbide, that is another offering that we have for other markets. Exactly. Typically not necessary for motor drives, but it is there. And then I have an interesting question about, are these modules available on the website?
No, not at the moment. Most of them you can sample, so you have to reach out to us and talk to us, and then we can provide samples, and from there we go.
Okay. And then a question: can you reveal all of your suppliers?
We'll not reveal all of our suppliers. But the most important I mentioned now a few times, for these modules, it's ROHM that we partnered up with, and for other modules, it's other suppliers. Yeah.
Okay. Let's see. I think that was most of the questions here. It's also reaching about that time. So I'll say to the audience, thank you very much for joining our webinar. Carsten, thank you very much again.
Thank you.
I hope everyone could take some useful information away. And if you have further questions, please contact us at webinar@semikron-danfoss.com. Thank you and have a great day. Bye-bye.
Thanks. Bye.